Okay. It is 2:01. So we are going to go ahead and get started with this. Everyone, thank you for attending. Welcome to our webinar on advancements in image cytometry with high-speed cameras. Kyle will be taking you through the presentation today. It's going to be about 20 minutes long. And then we're going to go ahead and have a question and answer session at the end of it. If you do have a question that you would like to ask Kyle at the end, go ahead and use the chat section. I just ask that you please type the word question in front of it before you actually list out your question. It just helps me to be able to see that this is something you want to ask Kyle at the end of the session. So I'll be keeping track of those. And once that's done, he will answer any and all questions that you have. We do compile all of the questions, and we will create a page online that you will be able to access in order to review them if you missed any answers or you want to get a little bit more information. And also, once the webinar is complete, I will be uploading a video of it to a private URL and I will be sending an email out to everyone so that you can have access to said video and share it with others or watch it a second time if you'd like. So without further ado, Kyle, it is your turn, and everyone, enjoy the show.
Thanks, Kenny. Can you hear me okay?
I can. Sounds great.
Perfect. All right, let's jump right into it. Welcome, everybody, to our webinar on advances in image cytometry with high-speed cameras. So what we're basically going to talk about today is just a really basic introduction to what is image cytometry, okay, and talk about some of the challenges in terms of some of the imaging that's done here, especially in fluorescence imaging. It's going to naturally turn into a conversation between a trade-off of signal-to-noise ratio and motion artifacts. Then we're going to talk about kind of a movement in academia, kind of away from labeling and toward label-free cytometry, involving the use of bright field imaging and spectroscopy. I'm going to give some examples from the academic literature. That's from the past decade or so. I'm going to also talk about kind of the future of imaging hardware and how some of the new hardware elements are going to overcome some of the challenges that people face today. That's going to involve kind of discussion on classical high-speed imaging architectures, and then evolve into discussion on new age streaming-based cameras and some of their advantages. Okay, so what is image cytometry? All right, it's a technique to digitally image individual cells in a population in order to extract key physical and chemical features of those cells. Okay, so a basic concept on a very, very high level is you have cells in a suspension, right? Just cells in a liquid media. They're going to be syringe pumped into a microfluidic device. These microfluidic devices have one or more microchannels in them. These cells will traverse that microchannel, and then there will be some optics, excitation, and sensors to capture images of this event as they travel through this microchannel. Okay, and what you get as an output in general for commercial cytometers capable of doing bright field inflorescence is you get a beautiful bright field image together with a variety of different fluorescent channels of the individual cells, right? So each cell that flows in there, camera takes an image of it, and you get this great library of cellular information, okay? And what do people do with that, right? Ultimately, what they want to do is a diverse set of applications, whether it be just counting certain cell types, getting size information, shape, morphology. Maybe they want to do some identification of a cell type. Maybe they want to diagnose a disease state. They want to study gene expression or some type of DNA-related phenomena, right? Some people want to look at the elasticity of cells as they travel through these channels. And some people even want to make informed decisions on those cells as they go through. For example, maybe they want to sort them or destroy them as they're going through the microchannel, right? And if you look at the academic literature, there's a lot more examples of what people want to do. All right, so from the standpoint of imaging, all right, if we think about fluorescence imaging and we want to learn why it's such a struggle to go to high speeds when imaging. Okay, if you think of an individual cell, okay, and you imagine that that cell has a fluorescent marker on one particular aspect of the cell. Let's just consider it to be a labeled organelle, all right? And it has a fluorophore attached to it, bound to it, and then we excite that region with an excitation laser. Okay, what that'll do is it will elicit a fluorescence response. We'll get photons emitted isotropically from that site, okay? And what will then happen is we use some imaging optics to capture a small cone angle of that emission event, and we will take that image data and send it to our imaging optics. All right, now fundamentally, when you do this, the photon count relative to other experiments is relatively low. And why is it low? It's because that region is very, very small, right? We're talking about, you know, anywhere from 1 to 10 microns of feature size, right? So you get a very low amount of signal coming out of there. The emission itself is generally isotropic, right? So you get photons emitted in all directions, but you only can capture a small little piece of it as they come out. There's a limitation on the excitation power you can pump into a cell, right? You could increase the excitation power to optimize the amount of light emitted, but you can also get things like photo bleaching, or you can destroy your sample by overheating it and just completely destroying the cell, right? And then there's going to be inefficiencies and losses in the optical system, whether it be from quantum efficiency at the CCD or CMOS sensor. You could have optical losses due to reflections or scattering from lenses or mirrors and so on in your optical system, right? So fluorescence is a low photon event, okay? The other challenge is when you talk about high-speed imaging is the hallmark of high-speed imaging is the faster you go, the less light you can collect. All right, so if you think about it like this, imagine you had a frame rate of 1,000 frames per second. Let's say each one of these blue squares represents a frame, okay? So whenever you run the camera, it's gonna have a maximum integration time, which is integration time is basically how much light you allow the camera to be open to collect photons, all right? It's gonna be simply 1 over the frame rate. So you're gonna have roughly a millisecond or 1,000 microseconds of integration time, right? So that's 1,000 frames per second. Let's say you multiply that by 4, you bump it up a little faster, right? The maximum integration time is gonna be divided by 4 compared to the 1,000, right? So you're gonna have 250 microseconds. And then you can keep on playing this game, right? So you go up to 8,000, you're gonna get less and less integration time per image, right? So what you have here is, as you go faster and faster, you get lower integration times, all right? Now, the other issue you have when you're looking at single cells traveling very quickly through a microchannel is you have something called motion blur, all right? So essentially, when the cell moves through that channel, it's gonna be moving at a very high rate, okay? And if that rate is fast enough such that there's substantial movement relative to the integration time and pixel distance on the surface, you're going to have a motion blur. And the blurring distance is directly related to the velocity of that cell times the exposure time or effective exposure time of that imaging system. All right. And a schematic that I like to reference is if you have, for example, a cell moving through a microchannel, here's image 1 or frame 1, and here's frame 2. Okay. This blur distance is going to be your motion blur. Okay, and that's the amount of time the cell moves during frame capture. All right, so that's actually a huge problem when it comes to fluorescence imaging. So now if we put that all together and we really think about what that gives us, all right, and we try to understand how a pixel works on a CMOS sensor or a CCD sensor, is essentially you have all this light coming from your fluorescent event, right? It's a little bit of light, all right, and then it hits your pixel. All right, and you're going to have a given watts of photons, and it's going to create a given amps of electrons. All right, and if you look at the response of most scientific grade imagers, what you're going to see is there's going to be a linear response between the number of photons that you collect at your pixel per image relative to the total signal. All right, so naturally, if you have lower amount of photons, you're going to have a lower signal. If you have a longer exposure time, you're going to be able to collect more photons, assuming that you have a constant flux of photons over time, right? So here's what we're left with. The total signal you get on your pixel or on your sensor is going to be proportional to the amount of exposure time of that system times the photon flux, right? So this puts us in dire straits because as we saw, very high frame rates lead to very short exposure times, and fluorescent events have very low amount of light coming out of them. All right, so let's look at what the data shows us, right? So this is some data from a 2020 Nature Communication paper where they looked at two different types of cells in this example, right? And they just took a camera and they imaged it in fluorescence mode, and they set the exposure to 3 seconds, which is very, very long, right? So you get this image here of a static cell sitting there, right? So if you flow that cell now, right, at 1 meter per second, right, and that's considered fairly quick in the world of flow cytometry. People I've seen flow up to 10 meters per second, right? So if you even lower the exposure substantially down to 340 microseconds, right? This is the amount of time the pixel is open to collect light for. You see that you have pretty dramatic motion blur, right? And yeah, this is good information to tell you kind of what fluorescent information is there, but you get no information about the morphology or shape of that cell, right? So you get horrible motion blur. So naturally, scientists, what they'll do is to say, oh, all right, I have motion blur. I know what this is. Let me just lower my exposure time to get no motion blur. What happens? You eliminate your motion blur, but you're left with essentially no signal because your exposure time, your signal intensity is proportional to your exposure time, right? So there you are. You're stuck in this battle between signal to noise ratio and motion blur, right? So that's the fundamental issue, all right? So how do you overcome these two things, right? These motion blur and this signal to noise ratio issue. The commercial method that folks use is something called time delay integration. And the best example is to start off with how a normal global shutter sensor works, right? So on the left here, if we have a fluorescent particle that flows across the sensor, normally what happens in a standard high-speed camera is it just takes one image, right? And you get a single exposure. And in that region of interest, you get this fairly low signal to noise ratio image of this fluorescent particle, right? Now, what clever sensor engineers have done is they came up with this idea of TDI, or time delay integration, where as this cell flows across, what they do is they delay the integration time across the sensor. So you have the cell here, the image data flows off, and then you have the image here, flows off, and so on. Okay, so now you have essentially the same image at different regions of the sensor that get read off at different times, at the delayed periods of time, right? And there's some other magic that goes on to make sure that the readout is optimal for the speed of the cell and also the size of the cell and so on. But what that allows you to do is get higher signal to noise ratio because you can essentially do an average of these images, right? So that's kind of the state of the art methodology used in commercial systems like that seen in, for example, image cytometers like you see here, where you have a laser or a light source hitting your flow channel, and you have a forward scatter detector, and you have a series of side scatter detectors to collect your fluorescent emission, right? These are your fluorescent channels. And then they employ the TDI to essentially get really nice signal to noise ratio of your fluorescent channels, and in some cases your bright field images. Okay. Now there's even folks looking to move past the use of TDI. Okay. Here's an example from a 2020 Nature Communication article where what they did was they used a polygon scanner, which is basically a rotating mirror system. Okay. And what that allows you to do is, as these cells flow through the microchannel, what happens is the image is projected onto this scanner. And then due to the rotation and the planar nature of this scanner, it will actually move your image relative to the sensor. So you can actually freeze the motion. And at the same time, they'll have a beam scanner and light sheet excitation to minimize the motion blur due to the cell motion here. Okay. So what they have here is they have these cells going through a microchannel over this field of view. Okay, and they basically scan a beam across there. All right, so if you did this without the scanner on, you'd get exactly what you saw previously, where you have this pretty dramatic motion blur. However, when you start to basically rotate the polygon scanner, it will basically move the field of view in such a manner that the cells are frozen for a short period of time, even though they're moving at high speeds. Okay, so this is projected onto the sensor face. All right, so here's some examples that they show. Even at 1 meter per second flow speed, which seems to be a kind of a benchmark speed that people use in the literature, they get beautiful data in terms of the signal to noise ratio of the different fluorescent channels. And they did this for a variety of different cells. So this is a pretty interesting technique that people are using. Another area we've seen a lot of, oh, would you mind muting your microphones, please? I hear some feedback, thank you. Another interesting area is people integrating high-speed cameras with image intensifiers. Here you see a high-speed camera hooked up to image intensifier, which is then hooked up to a microscope. So essentially what you have here is the same setup you would have with a normal imaging camera, except now you have the upgraded image intensifier and camera, right? So what this allows you to do is, as that image flows out of the microscope, this image intensifier will dramatically boost the signal that's coming out of the system. And essentially what you're doing is you're going from photons to electrons, you're amplifying the electronic signal, and you're putting it back into photons to project onto the high-speed camera here, and you're able to get really nice high-speed video, even when the events are considered a low light event, right? So an example of that here is, here's a control experiment that we did in collaboration with some of the image intensifier partners. And what we had here was a 5-micron fluorescent bead at 10x magnification. And we just simply increased the frame rate to see what the signal to noise would look like. So without the intensifier, you can see at 1 kilohertz, 10 and 30, you can see that you get very, very low signal to noise ratio. It's that little dot there in the middle. All right. And then when you incorporate an intensifier into the mix, what you see is you can run at really high frame rates. So at 10 kilohertz, 100 and 300, you get really nice signal to noise ratio with that image intensifier, right? So there's a lot of advantages that come from just the integration of the image intensifier, right? So there's no need to use TDI, right? You can use a global shutter that's intrinsic to the high-speed camera, all right? There's essentially no moving parts, right, outside from the fan and the camera, so you get some benefit there. You can operate the system at the frame rate of the camera in general, all right? Generally, these intensifiers integrate with the TTL logic of the camera, so it will synchronize with the frames of the camera. Okay, so you get good signal to noise ratio at really high frame rates. You get ultra low effective exposure times. Even the high-speed cameras in general have really nice exposure times, and you can even utilize the gating feature of intensifiers to get even lower effective exposure times. And it's fairly easy to integrate with the camera. All right, everything's adaptable and available. And as you can see, it can be readily mounted on with the camera and a microscope pair. Okay. And the other interesting thing is, and I'll talk about this in a little bit, is that these systems also work with standard and machine vision high-speed cameras as well. All right, there's even been a push away from fluorescence imaging and more toward bright field imaging, just because people are finding out that they get a lot of information just from the bright field image itself. Okay, so what does a bright field setup look like? It's nothing more than a high-speed camera integrated into a standard microscope, and that microscope is looking down into a microfluidic chip here. Okay, here's a close-up view of it. And then this microfluidic chip is backlit using a fiber LED. And essentially photons go through the sample, and then the refractive index gradient of the cell environment will create contrast onto the image sensor. Okay, so the camera integrates directly into that microscope just with a C-mount adapter. All right, plugs right on in. So what people are doing here is there's been a recent push toward label-free cytometry. So in this case here, they have a syringe pump filled with cells, just like you would during a normal image cytometer setup. And they push it through a microfluidic channel. They have a high-speed CMOS sensor down here with a high-power LED. This could be upside down if you wanted it to. In general, people work between 10 and 60x magnification. And then they flow the cell through a microchannel. And in this particular Nature Methods paper in 2015, what they did is they simply flowed it through a very narrow channel, and they wanted to correlate the deformation to the size of the cell as it goes through there using this setup. Okay. And then what they did is they did simulations to better understand how the elasticity related to this deformation. Okay. So they basically created some trends, and they related the cell size to the degree of deformation. And then they can learn about the average elasticity of that cell as it flows through the channel. All right. And the ultimate goal of what they want to do is they want to create this phase map, right? And they want to relate the cell type to the initial diameter and the deformability of that cell, right? So if you have a particular type of cell, right? If it's, let's say it's a big old flimsy cancer cell, it's probably going to have a big initial diameter and it's going to have a pretty large elasticity constant here. Okay, so it'll sit up here on this phase. If you have a small and rigid polystyrene bead with a small size here, it's going to have a very low deformity, low elasticity, and small diameter. So it'll sit here on the phase map, right? So that's the general idea of where people are going, right? So this is straightforward, high throughput, broad applicability, and label free, right? There's no need to stain your cells, tag them with fluorophores, and potentially kill the cells, right? These can be potentially even done in vivo, all right? And if you look at this 2012 review paper, they've demonstrated that this is viable for characterizing the phenotype and cell state for cancer malignancy, slight cytoskeletal changes, okay, cell differentiation, and beyond. All right. A lot of interesting work came out of the DiCarlo group at UCLA. All right. What they did is they flowed cells into a really interesting microfluidic chip. All right. They have cells entering into the chip from the left and the right, and the exit is in the top and the bottom. And when they enter into this region in the middle of the chip, the cell will essentially stretch out. It's like hitting basically a wall here, okay? And it'll flow up or it'll flow down. But what they did was they flowed the cells at very high rates. And here's basically a cell, a standard cell being pushed through here, a cancer cell. And as it entered in this region, right, this is 1 frame, 2 frame, 3 frame, and so on, the cell stretched out, all right? So what they did was they correlated the initial shape of the cell to the deformability of that cell in that stretching region. And they could create essentially a phase map like we just chatted about, all right, where they have the initial diameter of the cell, and then they have the deformability or the aspect ratio essentially mapped on the y-axis, all right? So really interesting. What they did is they captured 5 frames as it went across. They ran the camera to 142,000 frames per second at a very narrow resolution of 256 by 32. All right. And as a sanity check, as you can imagine, they flowed polystyrene beads to start, right? Very rigid, small particles. And then they can essentially calibrate their system, make sure there's no funny business going on, right? Here are the cells going, or the beads going through at a very high frame rate at a 1 microsecond exposure time. So that's just some example data. Okay. Here's one small video of an undifferentiated stem cell. And what they showed is that as it goes in there, you can see some stretching phenomena and it goes out, right? And that can be repeated for hundreds of thousands and millions of cells as they go across, okay? So another interesting area is people flowing cells against rigid structures. So just like the setup before, you have a sample fill of cells, flow them across your microfluidic channel. And what they did is they have a region where the cells are coming in randomly, and then they have a region of their microchannel that's stepped. So this will align them and space them out. And they also have a space chamber where they really get them well spaced relative to one another. And then finally, they enter into this region where they smack against a wall, okay? And then they can get the deformability of that cell as it smashes into that wall. Okay, so here's some really interesting data from that. These cells are flowing at 4 meters per second, so very fast, and they're being captured at 100,000 frames per second at a 1 microsecond exposure time. right? And again, this can be done for many, many cells, and you can get really interesting statistical information from that. All right, and you can even do clever things like relate the deformability to the cell size and elasticity constants. All right, so they did their due diligence and they did some simulations on that cell. We have some people pushing the limits of high speed in real time. All right, so in some cases, what people want to do is they want to do some type of action on the images as they come in. All right, so in this case, what they did was they developed a script. They used C++ and OpenCV to automate their process. So they're able to control the camera and flow all using an SDK. All right, so the camera can completely be controlled by C++, Python, or LabVIEW, or whatever, whatever you wanted to control it with. All right, and then they utilize an FPGA to a local hard drive just to optimize the processing rate of the data coming off. Okay, so that can all be done, right? But one of the bottlenecks that came of this, right, is the fact that commercial high-speed cameras generally need to save the data locally to a RAM buffer before they can be processed. And that's just an inherent limitation of high-speed cameras. All right, so in this case, we have many people using, for example, a V2512 for image cytometry. So that's simply a CMOS sensor that writes all the image data at 25 gigapixels per second to a local volatile memory RAM. All that data is written to the RAM, and then it's saved off the back of the camera over GigE. Okay, all your image data is saved off, right? And by 10 GigE, you can save less than around 10 gigabits a second, where if you're downloading the whole RAM of the camera, this could be seconds up to minutes of download time. Okay, a new strategy that has been incorporated, although starting off in the mid-range speeds, we have high-speed machine vision cameras, okay? And these are designed to flow the data off the back of the camera, okay? So there's no onboard RAM on the camera, and all the data can be written to a back-end PC, okay? So it flows into a CXP frame grabber card and then into a back-end PC, okay? Vision Research just came out with a new technology that replaced the copper with fiber. So you can basically reduce the number of cables and the efficiency of your setup just by using the machine vision cameras. So ultimately what this allows you to do is you can do real-time image analysis. You have access to the images on the fly, and you also have the ability to do long-time records, okay? So the back end is completely customizable by the user. All right, here's an example of that. This is a piece of software written by the company Spica Technology, or Spica Tech. And what they did is they integrated the camera into a microfluidics system, okay? And polystyrene beads were flowed at different sizes. And these images were processed absolutely on the fly, and it can report the size, shape, color of all these cells as they move across the channel. And this is done by using the machine vision cameras. Okay. I know this was a very short webinar. I hope you guys learned some things. If you want some more information, helpful content on image flow cytometry, Andy Philby is a fantastic lecturer. He has a talk in iBiology. I recommend you take a look at that. There's also a free book online called Image Flow Cytometry, where you can learn a lot of the fundamental concepts in there. I'm happy to take any questions. We have some white papers available. You can follow the link below, or you can ask some questions right now. I'm happy to answer them. Thanks for listening.
Okay, thank you very much, Kyle. We did not have any questions come in. Did anyone have any last minute questions they wanted to ask? Or if not, then we can just kind of shut it down and call it good. As I said before at the start of this, there will absolutely be a link that is sent out to everyone that will link to a recording of this webinar. So you'll be able to review it or share it with anyone that you would like to. If you have any questions, you think of something later, you are more than welcome to use the contact us form on our website to submit the question through to us, and we will definitely have Kyle or another one of our field application experts get back to you with an answer to your question. We also encourage that if you're interested, you could contact us for a possible demonstration. We do a lot of travel work with both new and current customers to make sure that the system that you're looking at is the right avenue for your research and that you'll be getting the most out of the camera that you're looking at. So other than that, I don't have any questions coming in. So Kyle, thank you again. Everyone that attended, thank you very much for watching, and we'll go ahead and call it a day.
Yep. Have a great day, everybody. Bye.
Have a great day.